Hello, welcome to this lesson. This is 1B.6. We're going to talk about end behavior of rational functions from symbolic or analytical form. Now, we have already talked about, up until this point, about end behavior of rational functions graphically, so we're going to build on that idea, and we're going to go ahead and specifically look at determining the end behavior from the leading terms. Now, this is going to require us to be able to simplify the ratio of two leading terms, which includes two monomials. So I want to refresh your memory on a couple of exponent properties. Remember, if you are dividing two variables with powers, you end up subtracting those powers. So if I have the structure of a to the power of m over a to the power of n, this is just a to the power of m minus n. Or subsequently, and we often see this when the degree of the denominator is greater than the degree in the numerator, we end up with 1 over a to the power of n minus m. And then just recall that if you have a to the power of 0, that just is 1. Anything to the power of 0 is 1. So let's go ahead and look at some of these concepts here. We're asked to simplify the expression negative 3x to the fifth over x cubed. Well, I have negative 3x to the power of 5 minus 3, which just gives us negative 3x to the power of 2, right? So that's that first property that we see here. We essentially cancel the x's. Example number 2, we have 10x to the power of 3 over 4x to the power of 4. Again, here I'm going to reduce the 10 over 4 to be 5 over 2. And I have x to the fourth and x to the cube in the numerator. So here's that situation where I would do this. X to the power of 4 minus 3 gives us 5 over 2x. Okay, and again, essentially we're just canceling out x's. That's the easiest way to think about it. And then lastly here, I have 2x to the fourth over 4x to the fourth. Again, I can reduce here. I have a 1 in the numerator. In the denominator, this reduces to a 2. And x to the fourth and x to the fourth, these cancel out. This essentially gives you a 1. Another way to look at this, right, would be to think about it as x to the fourth minus x to the power of 4, which gives us x to the power of 0, which is just 1. I kind of like the idea of just canceling terms out, thinking about it that way. Okay, so now that we've gone through the intent of the lesson, how you'll be successful in some foundational skills, we're going to go ahead and talk about some vocabulary terms that you'll need to familiarize yourself with and the concept. Remember, a rational function is just a ratio of two polynomial functions. The end behavior of a rational function will be most affected by the polynomial with the greater degree as inputs get really, really large, either in the positive or negative direction. Therefore, the end behavior of a rational function can be determined by examining the ratio of the leading terms of the two polynomials. Now, from a previous lesson, we have already talked about the three cases that arise when you have a rational function. You can have the case where the term in the numerator has a bigger power than the term in the denominator. We call that case big over little. And I'll abbreviate that off to the side over here, B over L. And that's what this first case says. It says if the ratio of the leading terms has the form a times x to the power of n, then the end behavior of the rational function will be the same as the end behavior of the polynomial function with the leading term a times x to the power of n. And if that polynomial is linear, then the rational function has a slant asymptote parallel to the graph of the line. Now, in all the cases we've seen before, our slant asymptotes have been linear. We're going to kind of break that trend where our ratio of our leading terms simplifies to a non-linear term. Okay, so that's case 1, big over little. Case number 2, which is the most common with rational functions, is we get little over big. And so if the leading terms has a ratio of the form a, where a is a constant, over x to the power of n, then r of x has a horizontal asymptote at y equals 0, and the end behaviors will both be 0. Our rational functions will approach that horizontal asymptote. And case number 3, we have same over same. If I have my leading term ratio, the leading terms has a form of a constant, right? Because if it's same over same, the monomials will cancel out. Then the rational function has a horizontal asymptote at y equals c, and the limit will approach c at the infinities. Okay? So we're going to look at some examples in a second, but I want to remind you about polynomial n behavior, which is really tied to case number 1, which we said here, big over little. And just remember that the n behavior is determined by first, I like to think first the sign of the leading coefficient. This will tell you what your right side is doing, what the right side is doing, and then the degree. This will tell you what the left side is doing. If it's an even power, they're going to match. If it's odd, it's going to be the opposite. And so here we have some examples. Just note here they say if a is greater than 0, that means you have a positive coefficient, then your right side's going to go up. Okay, right side's going to go up. And if it's even, then it's going to match. So notice how they match. Okay, if your a value is negative, if your leading coefficient's negative, right side's going to go down. And then again, if it's even, the left side will match. Both will go down. In the odd case, again, if your leading coefficient is positive, right side's going to go up, and the left side, since it's odd, will do the opposite. And again, if my coefficient is negative, right side's going to be negative, going to go down, and our function is odd, the left side will do the opposite. So let's go ahead, let's look at example number 1. The function g is given by g of x equals 8x squared plus 5x over 3x minus 1. Again, this is similar. What we care about most here is our leading terms, and I like to just make an approximation of 8x squared over 3x. And if I reduce this, I get 8/3 times x. Okay? Now this is a linear function if I look at this. This is definitely big over little, so this is a slant asymptote, and that slant asymptote, the end behaviors are going to behave like this 8/3 x linear function. Okay? So what does that mean? Well, it means my right side's going up, left side's going down. Question. Determine the end behavior of g as x decreases without bound. Express your answer using the mathematical notation of a limit. Okay, so I have the limit of g of x as x decreases without bound, as x goes to negative infinity. So the left side here is going down. And again, how we read this, the limit of g of x as x approaches negative infinity equals negative infinity. So practice saying that. Practice reading this next one. Okay, example 2. Determine the end behavior of g as x increases without bound using limit notation. The limit of g of x as x approaches positive infinity is equal to positive infinity, because that's what my right side is doing. Okay, pretty straightforward. Example 2. In this case, my numerator is a 6. That's my leading term. The term in the denominator, the polynomial, is in factored form, and so in order to determine my leading term, I'm going to multiply the leading terms of all the factors. So essentially the leading term of my denominator in standard form will be x squared. This is little over big, which implies that d has a horizontal asymptote of y equals 0. And if I have a horizontal asymptote, my rational function will approach that horizontal asymptote at the infinities. So I can go ahead and answer these questions here. The limit of d of x, they want as d decreases without bound. So that's x approaching negative infinity. It's going to be equal to 0. Both sides will go to 0. Example 2, the limit of d of x as x increases without bound. That's x going to positive infinity. Again, it's going to approach 0. Okay? The only case that I did not show you is same over same, where they would have a horizontal asymptote at a value. Okay? And I'm sure you're going to see this in some practice problems coming up. Okay, some practice problems here. Please go ahead, pause the video, try this practice problem, and then I will show you the solution. All right, hopefully you tried this one. Your leading term, not sure why there's an R there, but your leading term here is going to be negative 5x to the power of 3 over 4x, which reduces to negative 5 over 4 times x to the power of 2. This is going to be a downward facing quadratic. Looks like this. So your answer would be the limit of p of x as x approaches negative infinity, because we're decreasing without bound, is negative infinity. Both sides are going down. B, the end behavior of p as x increases without bound, well, that's also going to be going down. The limit as x approaches positive infinity is negative infinity. Not too bad. Just look at your leading terms. Leading terms will tell you the end behavior. All right, here is example number 2. Please try this one. Please note your denominator is in factored form, so you're going to determine that leading term. Try this one. I'll show you the solution here in a second. Okay, hopefully you try this one. Again, your leading term is 9x squared. In the denominator, 6 times x is 6x squared. And these cancel, and we reduce to 3/2. So our answer, the limit of r of x as x goes to negative infinity is equal to 3/2. That's the horizontal asymptote. Y equals 3/2. For part B, the limit of r of x as x approaches positive infinity is equal to 3/2. All right. I have some multiple choice questions for you. Please go ahead, pause the video, try these multiple choice answers, and then we'll go ahead and talk about them. All right. Hopefully you tried this one. The answer for this is, drum roll, B. B is the answer. The reason is this is factored form. They give you a function m, and they say which is equivalent to m of x equals b over d, where b and d are polynomials, which the following statements is true. Well, in order to determine the limit as x approaches positive infinity, I need to know what's the end behavior look like. So we're going to take the leading terms, 2x times 3x times x. So m of x is approximately equal to 6x to the power of 3. And in the denominator, I have x times 2x squared. Usually the 2x squared is what gets people, because 2x times 2x is 4, and then we have x to the power of 3. So this is equal to 3/2. All right, next practice one. Please go ahead, pause the video, try this practice problem. All right, on this example, the rational function n is given by n of x equals x to the power k times x plus 2 times x minus 4 over x to the power 6 minus 5x cubed plus 8, where k is a positive integer. Which of the following values of k will the graph of n have n behavior as the limit as x approaches negative infinity of n of x equals 1, as well as the limit as n of x as x approaches positive infinity equals 1. Well, when they tell you that the end behavior goes to 1 if it's a rational function, they're telling you that the horizontal asymptote is y equals 1, which would be the case of same over same. So we want our leading terms to have the same degree. So if I look at this, I have x to the power of k times x times x. So that's x to the power of k plus 2. And then in the denominator, it's already in standard form. So I want them both to have a degree 6. K must be b, 4. All right. Next practice one. Please go ahead, pause the video, and try this example. All right, here we go. The answer for this example is determined by looking at, the ratio of your leading terms. So k is approximately 2x to the power of 5 over x to the power of 3, which gives us 2x to the power of 2. So that's going to eliminate a, and it's going to eliminate c. So our answers are between b and d. And this is a positive quadratic. Positive even. So both end behaviors are going up. The answer, D. Answer is D. All right. Last. Please go ahead, try this example, and then we'll check your work. All right, so looking at our leading terms here, we have little over big. This is going to be approximately, big over little, negative x, which is a negative linear function, looks something like this. So as x increases without bound, that's what all of these are saying. So as x increases without bound, it looks like our function is going down. H of x is going to decrease without bound. So this is correct, this is correct. So b and d are out the window. And then let's go ahead and look at the next part. As x decreases without bound, h of x increases without bound. So yeah, A. A is the answer. All right, that did it for this video. Hopefully you learned how to determine the limit as x approaches positive and negative infinity for rational functions. All you do is determine the horizontal asymptote. That's it. All right, like the video, thumbs up. Catch you in the next video. See you later.